Algebra 2 Honors, Lesson 10.6, Exponential Growth and Decay. So, Lesson 10.6, Exponential Growth and Decay. Jump right in with examples. Caffeine is eliminated from your body at 11% per hour. You drink 130 milligrams, that's a regular cup of coffee. How long will it take for half the caffeine to be eliminated from your body? So the formula is y equals a 1 minus r to the t. A, of course, is the original amount. R, of course, is the percent eliminated per time unit, in this case per hour. And T is the time unit, in this case hours. So it's straight plug and chug from here. Y equals back up. How long it take per half? So 65 equals 130. 1 minus 0.11 to the t. 65 over 130 is 0.5. Call that a half-life. How long does it take something to become half of what it was? 0.5 equals 1, actually we can do this, 0.89 to the t. Take any log we want. In this case I'll use the natural log because that's going to pop up later. Natural log of 0.5 equals t, because we bring it out front when we take the natural log, 0.89. T equals, and I'm using the calculator here, natural log of 0.5 divided by natural log of 0.89. 5.95 hours. Actually, it's a log, so I'll go out all the way to that. So all we're doing now is getting used to practicing these. There's nothing else to say. This one I was given a percentage. How about this one? Do we get a percentage? It's a different type of exponential. Decay. Decay meaning going down, less. Carbon-14, which is used to date things that are incredibly old, it decays continuously at a fixed rate, and it's got a 5,760 years half-life. Now, I actually looked this up because they make it sound like it's so easy to just go, oh, yeah, so I just, find out how much carbon's left. Well, how do you know how much of it is less? And there's some really complicated chemistry goes in. A couple of people won Nobel Prizes. And as you can guess, it's not perfectly accurate. It's accurate within a couple hundred years, 50 years, depending on the test, depending on who's doing it, depending on when they do it. So I say to find the K value in this situation. And that means you need to see the formula. This is decay, exponential, no percentage given. So we want to know what the K value is. We have half-life. The original amount over 2 is the original amount. And K is a constant, depending on what we're using. So for carbon-14, once you figure it out, you don't have to do it again. E to the negative K times apparently 5,760 years will get us half. If I divide both sides by A, I end up with 1/2. So 1/2 equals E to the negative K, 5760. Natural log of both sides. I do not know why I keep doing that. I can bring the negative K out front. Natural log of E cancels. I get negative k times 57 equals natural log of 1/2. K equals negative natural log of 1/2 over 5760. Get a really small number, positive 1.2 times 10 to the negative fourth, 1.203, which is 0. Short of 0. 1, 2, 3, 4. There it is. So that's our k value. So now we can use it. How long does it take to get 3%? That's what it says right here. We do some math. We say, hey, it's 0.03 of the original amount. Divide out the a. Take natural log of both sides. Divide by negative 0.1231203. And it tells us approximately 29,000 years ago. So that's a second type of exponential decay. Now, of course, we will work on exponential growth. City has a growth rate of 1.5% every year. I think this is supposed to be Raleigh, North Carolina, or something like that. Or I might have made it up. What's population now? So what we do is we typically say this will be time equals 0. So population now is, the time now, 2015 minus 1910. It's 105 years later. The formula for this will look somewhat familiar. Original amount times 1 plus r to the t. I'm not going to redefine it, you already know. So we had 120,000 people times 1 plus 0.015 to the 105. We should have 572,948 people. And that's just an example of exponential growth. Things keep getting more and more. That's it. If you wanted to do it with the other formula, you would have to either know the k value or have some data on hand to find the k value. For example, here are the k values given to you for China, which had 1.26 billion people in 2000, and India, which had 1.01 billion people. India is on a steady increase. China's starting to top out due to their one-child policy, which they are considering relaxing, but they're not quite there yet. So there it is. Y equals AE to the KT, same information as before. We want to set these equal to find what T will equal what T is when they are equal. So let's divide by 1.01. And it's going to get a little dicey here. 1.2475. So I can take natural log on the right side, piece of cake, but natural log on the left side looks kind of ugly. What the heck are we going to do? Well, we've got actually, I don't know, remember something we did once. Gone, 0.015t. Two things are being multiplied inside. We can add them. 1.2475 plus, they cancel, 0.009t. Subtract 0.006t ln 1.2475 t equals ln 1.2475 over 0.126. And it says 36.9 years. Actually, I'll go one more. In other words, we should expect their populations to be the same in the year 2037, which shows you some degree of the limit of mathematics. This is 15 years ago, and we know it's actually going to happen much sooner than that. India has no reason to slow their population growth down. China already has. That's it. Good luck.